So in today's video, we're going to start delving into the applications of derivatives in different contexts. And the first application, probably one of the most important ones, is actually in physics with motion problems. And so what we're going to find is that we can actually describe different variables such as velocity and acceleration in terms of the derivative of position. And so let's actually go ahead and see what I mean by that. So over here, let's say that we have some particle that's traveling through space in the x direction. And so the way that we can represent kind of the position of this particle is, first of all, here we would have time as our independent variable, right? Because we're kind of varying in time. As time progresses, our position is going to change. And we can represent position as an x over here. So we would say that x of t would kind of be our position as a function of time. So the position of our particle as a function of time. And actually, this type of graph is kind of referred to as a position versus time graph. Right, so position versus time. I don't know why my pen is acting up. But anyways, this is our position versus time graph. And if we go back to our basic kind of physics in high school in grade 9 and 10, we have these different equations for the average velocity and average acceleration given a position versus time graph. So we know that the average velocity, which we'll denote by v, and we can even write v average kind of as a subscript, is given by the change in position, or the displacement, if you will, over the change in time. So, this d over here, we could use different variables for position and for distance and displacement. Sometimes you'll see s, sometimes x, y. It just depends on, which one you prefer and kind of the context of the problem. I'm just going to use x for the time being. But essentially, so we could even rewrite this as the change in x if you want. But, d is kind of known a little bit more universally as distance or displacement. But the average velocity is basically just the kind of slope of the secant line between 2 points. Let me show you what I mean by that. I mean, it's the slope of the curve between two given points. So if you want to find the average velocity between, let's say, these 2 points over here, then we would just go ahead and calculate the slope of this line. And so the slope over here, the slope of our secant line is equal to the average velocity over this interval. Average velocity. But then what happens if we want to figure out the instantaneous velocity, right? So let's say we want to figure out the instantaneous velocity at this point. So at this instant right over here, at this instant in time, what velocity are we traveling at that moment? So not kind of our average velocity over an interval, but the instantaneous velocity at a particular moment in time. And so we know kind of by definition that the instantaneous rate of change of a function is just given by the derivative of the function at that point. Why is that an arrow? It's not meant to be an arrow. Okay, so right over here, we would say that the slope is going to be equal to the instantaneous velocity. I don't know why my pen is acting up a lot. So the slope is going to be the instantaneous velocity at this moment, right? And the instantaneous velocity, or the instantaneous rate of change of a function, is just given by the derivative. So we can actually come up with one relation over here, that the instantaneous velocity is going to be equal to the derivative of x with respect to time, right? Because the way we can think about it is this change in x and this change in t are just becoming infinitely small, right? It's as the change in time approaches 0, then this entire term right over here is going to become a differential, right? And so we're going to end up with the fact that the instantaneous velocity at a given point is given by the derivative of position with respect to time. And so with that in mind, we can look at the definition of acceleration in terms of kind of velocity. So the average acceleration right over here, so this right over here is average acceleration, is given by the change in velocity with respect to time over a certain time interval. And if we look at a velocity time graph, it would just be the slope of the secant line of that. But then what happens when we kind of just want to figure out the instantaneous acceleration at one particular point? Then we end up with, again, the derivative of velocity at that point. So the instantaneous acceleration is given by the derivative of velocity with respect to time. And I mean, we don't really need to write kind of instantaneous as a subscript every time. We can just say v equals dx by dt and a equals dv by dt. But what is v, though? What is the instantaneous velocity? Well, we know that the instantaneous velocity is the derivative of position with respect to time. So we can go ahead and substitute that in. So dx by dt And now we're just taking the derivative of a derivative. So that's by definition just the second derivative of x with respect to time squared, I guess, or with respect to t. And so now we have three kind of equations of motion, or new equations of motion in terms of the derivative of position. So the first one that we have to kind of summarize everything is that the velocity is given by the derivative of position with respect to time. The acceleration is given by the derivative of velocity with respect to time. Or the acceleration is given by the second derivative of position with respect to time. So these right over here are three kind of very important equations of motion that we'll be using when we consider the applications of derivatives in physics.